Welcome to this lecture in our course on mechanical operations. In the last class, we started discussing fluidization, fluidized beds, which are involved in many separation processes and catalytic process and so on. And we looked at flow of fluids past single particles as well as flow through a packed bed of particles. And as I mentioned last time, it's also important to consider the opposite situation where you study the dynamics of particles as they move through a fluid. When a particle moves through a fluid, there is always an initial transition time when it's an unsteady process. So for example, if you drop a stone into water, for example, initially it will have a certain acceleration, and the acceleration will slowly die down until it reaches a terminal velocity, and then it will settle down, right. Usually this transition period is short, and therefore it's neglected in many studies. We had discussed the terminal velocity in one of the earlier lectures in the context of particle dynamics, but when you actually analyze how particles move through a fluid, it is an unsteady process, at least in the beginning. And so you have to write a force balance. That is essentially a force that is acting in the direction of flow of the particle, and there will be at least two forces opposing it. One is the buoyancy force and the other is the drag force. The force that's actually causing the particle to move can be something that is just based on the density difference between the particle and the fluid, like a gravity force or a centrifugal force, or it can be an externally applied field. For example, in an electrostatic precipitator, you use electrostatic charge and the field force associated with that as a way of causing the particles to move at different velocities and therefore get separated in this apparatus. So in general, that external force can be a non-gravitational force as well. Electric forces, thermal forces can induce thermophoretic velocities, magnetic forces if you have magnetic particles in your system and so on. But in general, the picture is you have a fluid and you have particles that are moving through, and so there is a force, let's just call it some Fe, external force, which is opposed by a buoyancy force and a drag force. So in general, the unsteady equation would say mp times du by dt equals Fe minus Fb minus Fd, and you have to solve this in order to find the time dependent motion of the particle as it moves through the fluid. Now, one assumption that we typically make is that the direction of motion of the particle and the direction in which the force field is applied are the same. In other words, if there is a gravity pull, you assume that particle moves vertically, but you can imagine many scenarios in which that may not be true. For example, simple case of a feather that's falling through air, gravity is acting in one direction, but the feather itself moves in multiple directions, right. So there are what are called two-dimensional particle motion laws, which take into account the fact that the applied field that's causing the particle to move and the resultant opposing forces are not exactly aligned in the same direction, but in general you can assume that they are. So Fe in general will be mass of the particle times some acceleration due to the applied force field. So here this can be simply g if it's a gravitational flow, or it can be omega squared r if it's a centrifugal field, or it could be various types of accelerations that happen in electric field, magnetic field, thermal field, and so on. So this AE can take multiple values depending on the actual flow environment. Fb, based on the Archimedes principle, you can say that mp by rho p is the volume of the particle. So this will be the volume of fluid that's displaced times rho, which is the density of the fluid, and you assume that the acceleration is the same, and so you write this as mp by over rho p times rho times AE. And finally, the drag force. Of course, the drag force is written in terms of a drag coefficient times half rho u squared times a projected area of the particle that's perpendicular to the direction of the flow. And so you substitute all this into the main equation and you can get a general expression for the flow dynamics of a particle. Now, as we have seen before, CD itself has a certain dependence on Reynolds number. For Reynolds number less than 1, you get what's known as Stokes flow or creeping flow, and CD is related to the Reynolds number as 24 by RE. But if you go to a sufficiently large Reynolds number, 1000 and above, up to about 200,000, you are in something called the Newton's regime. In the Newton's regime, this value of CD is essentially constant, and CD is approximately equal to 0.44 for spherical particles. Now, this value of AP, of course, for a, again for a sphere, it's 1 by 4 pi dp squared, and MP is 1 by 6 pi dp cubed times rho p. So you can, substitute these expressions. Of course, this has to be equal to 0 when you reach terminal velocity conditions, and this gives you the terminal velocity ut. So you can get an expression for ut in terms of, for a perfectly spherical particle, in terms of dp and rho p parameters, again by substituting. Now, when terminal settling happens, there are two phenomena that can counteract it. One is something we have discussed earlier in particle transport, and that is Brownian diffusion. As the particles are trying to settle down, if they are fine enough, diffusional phenomena also become important. So instead of simply drifting down vertically, they also start drifting randomly in sideways motion. So the behavior of particles in the fluid becomes 3-dimensional in nature, and there is essentially a statistically random process that goes on which dictates how the particles move. So the diffusional coefficient of the particle becomes an important parameter, and you have to compute its effect on particle motion. In general, thermal diffusion will slow down particle settling unless you have set up a thermal field in order to aid settling, as in a thermal precipitator. The other phenomenon that can affect settling, of course, is hindered settling. Hindered settling happens when the particles in suspension are close enough that they affect each other's settling characteristics. Now, it does not mean that they have to be physically in contact with each other. What it means is the particles should be close enough that they affect their nearest neighbors, or they affect the velocity profile or the velocity distribution in the vicinity of the nearest neighbor. So you can have what are called proximity effects. As long as two particles are close enough to each other, they will affect each other. And in fact, the settling velocity, when you have hindered settling, is given by ut to the power times epsilon to the power n, where ut is the terminal settling velocity in the absence of hindered settling. Epsilon is the void fraction. So 1 minus epsilon is the solids fraction in the suspension, and n is an exponent which varies between 2.5 to 4.6. In fact, if you take that same curve and you plot this value of n as a function of Reynolds number going from 0.1 to 1000, this has a behavior that kind of looks like this, where here this is 0.46 and or this is 4.6 and this is 2.5. Hindered settling affects large particles differently from small particles. In which case do you think hindered settling will have a greater effect? Will it have a greater effect for small particles or greater effect for large particles? How many think small particles? And why is that? Any idea? It's actually based on the boundary layer effect. In the case of small particles, the thickness of the boundary layer compared to the size of the particle is significant. And when we talk about two neighboring particles affecting each other's motion, what we are really talking about is the interference between the boundary layers that surround them. So, the more prominent the boundary layer, the more prominent the effect of hindered settling. A large particle, by comparison, has a relatively small boundary layer, and therefore, two large particles that are separated by the same distance are likely to have less of an intrusive effect on each other compared to two small particles. The other reason, of course, is small particles have a greater mobility because of diffusional characteristics. So, it is more likely that two adjacent particles will eventually physically come in contact. I mean, basically the propensity or potential for sideways motion or three-dimensional motion is greater for finer particles. So, in fact, in the case of fine particles, the hindered settling velocities can be as little as 1/10 of the settling velocities in the absence of the hindering. So, it is very important to take that into account. Although eventually what can happen is when particles in a fine particle suspension get close enough together, they start agglomerating. So, they become larger in size and then their settling velocity increases. So, hindered settling is not something that happens monotonically. After a certain point, once the concentration of particles increases to a level where agglomeration becomes likely, then settling can again speed up. Okay. The other parameter that is of interest is in any suspension where you have hindered settling happening, the viscosity of the suspension is also affected by this process, and in fact the expression for mu s compared to mu is given by 1 plus 0.5 epsilon divided by epsilon to the power 4, again epsilon being the void fraction. So, the viscosity of the suspension is also affected by the void fraction of the suspension, and of course, the viscosity also plays a role in dampening the motion of the particle. So, the particle will reach its terminal velocity faster in the case of more viscous solutions compared to less viscous solutions because of dissipation effects basically. So, hindered settling is something that you have to deal with all the time if you are ever in an industry that uses batch settling or sedimentation or any process that involves settling of particles. So, it is important to be aware of its potential consequences and design your process to take that into account. Okay, now going back to our discussion of the terminal velocity, as we have seen before, the terminal velocity takes a certain form in the Stokes regime, right. We wrote that expression in one of the earlier lectures. So, in the Reynolds number less than 1 or Stokes regime, CD equals 24 by RE, and if you write the expression for a spherical particle settling under Stokes flow conditions, it comes out to be UT equals what, rho p or g times dp squared times rho p minus rho over 18 mu, right. Dropping the Stokes-Cunningham correction factor for now, this is the expression for a spherical particle settling under Stokes conditions. In the case of Reynolds number that is between 1000 to 200,000, which is a Newton regime, the corresponding expression CD is equal to a constant, and as I mentioned earlier it's about 0.44, and if you substitute that and calculate the expression for ut, it looks like square root of g times dp times rho p minus rho over rho. So, the important thing that you need to realize is that you go for the dependence of ut on particle diameter goes from a square dependence for very fine sizes, I mean for very small Reynolds numbers, to a square root dependence for very large Reynolds numbers. Now, what is the practical implication of that? So, for example, if you take this this exponent for dp and you plot that against Reynolds number, what we are saying is at very low Reynolds numbers it is about 2, and at very high Reynolds numbers it is about 0.5. So, what about intermediate Reynolds numbers? What kind of shape do you expect? Do you think that basically it will be a kind of a straight line behavior, or this kind of behavior, or this kind of behavior? 1, 2, 3. 2. Why is that? Any particular reasons? Actually, the dependence is kind of almost straight. In other words, for intermediate Reynolds numbers you will get a dependence of roughly 1 as far as the particle diameter is concerned. So, here again you have to think about all this from a process engineer's viewpoint. As your Reynolds number changes, you have to realize that some of these dependencies are going to change. So, either you try and control the Reynolds number, which is one of the most critical flow parameters, or you try to allow the Reynolds number to vary, but then realize that some of these qualitative or parametric dependencies are going to change as the Reynolds number changes, and therefore you design accordingly. But how do you know in which regime you are? I mean, if you are in the Stokes regime, you know that a certain law applies, and if you know that if you are in the Newton regime, a different law applies. But how do you decide which range you are in? So, to do that you can kind of go back to this expression. Reynolds number is given by dp ut rho by mu. So, in order for, so you can basically in the Stokes, let us say that you are in the Stokes regime. So, you can substitute for ut as dp times g times dp squared times rho p minus rho by 18 mu times rho by mu. If Reynolds number equals 1, that means you are in the Stokes regime, right. So, just equate that to this and try to figure out what this means. So, this you can write as some dp cubed times some k, okay, and the value of k is everything else in this expression that excludes dp cubed. Once you know the corresponding values for the other parameters in this expression, you can calculate a value of k, and as long as the value of k corresponds to a Reynolds number of 1 or smaller, you know that you are in the Stokes regime. And similarly, in the Newton's regime, you can substitute for ut with the corresponding value of ut in the Newton's regime, and similarly find values for the set of parameters that will give you a Reynolds number in excess of 1000. So, by doing that analysis, you can estimate whether you are going to be in the Stokes regime, or whether you are going to be in the Newton regime, or whether you are going to be in some intermediate regime. Okay? And then based on that you can appropriately design your process. Now, where does this become important? Why is it important to know this? What type of an environment will have a change in Reynolds numbers over time to the point where you can go from Stokes to Newtons? A fluidized bed is a good example. Fluidization is essentially a phenomenon where you start with a fixed bed, a packed bed, where the particles are all stationary and distributed around a column, and you flow a fluid through it. Initially, what is going to happen is the fluid is going to flow, but the particles are going to stay in position. As you keep increasing the velocity of the fluid, eventually the particles themselves will begin to move, and they will start to become entrained in the flow. Then it will become sort of like the situations we have been discussing, which is movement of suspensions, movement of particles with a relative velocity in a fluid. So a fluidized bed is a combination of the two phenomena we have been talking about. You have particles that are fixed and fluid moving past them initially. Over time the particles themselves begin to move in the fluid. But in terms of the flow regime, what is going to be happening is you are going to be transitioning from a regime which is laminar or low Reynolds number to begin with, to a situation where the flow velocities are sufficient that the particles that are comprising the bed actually begin to get entrained and move with the flow. However, in a well controlled fluidized bed situation, what really changes are two things: the pressure drop and the length of the bed. In a fixed bed, there is a linear dependence between flow rate and pressure drop, right? If you try to achieve a higher flow rate, it involves a greater pressure drop. But in the case of a fluidized bed, that's not true. Increase in the flow rate does not necessarily imply an increase in the pressure. Initially it does. So if you take a look at delta P as a function of superficial velocity or u0, up to a certain velocity you get a linear increase in the pressure drop, but what remains constant is the length or height of the bed. Let us say this is the length column. In a fixed bed, as you keep increasing the flow rate, the pressure drop keeps increasing, but the height of the bed remains the same. In a fluidized bed, what will happen is that once you reach a point of fluidization, let us say it happens at this velocity, the pressure drop will become constant and the length of the bed will start to increase. It starts to expand basically. So in a fluidized bed, the bed accommodates the increase in pressure by expanding. Now, what are some advantages of a fluidized bed? The primary advantage is that you can go to higher flow velocities without paying a penalty in pressure drop. And where does a higher velocity help you? In one case, it improves the throughput. The more material you can pump through for a given time, the greater is your production capacity, so to speak. Whether it's cleaning up of a contaminated fluid or whether it's causing a two-phase reaction between one set of reactants that are in the fluid and one set of reactants that are in the catalyst bed, an increased flow rate enables you to produce more output. And if you don't have to pay a delta P penalty, that's good. But of course the design consideration is how do you manage the height of the bed? How do you essentially keep it operating in a steady state manner? How do you reach steady state and how do you maintain that in a stable state? And here is where the characteristics of particle behavior in suspensions helps us. It is essentially a self-limiting process or self-regulating process. Particle motion in a fluid wants to reach a steady state equilibrium, and therefore there is actually a driving force. The farther away it is from an equilibrium condition, it tries to proceed to that equilibrium condition faster. And so the transient behavior as it tries to approach this equilibrium is quite strong. So the basic behavior of a fluidized bed, particularly in terms of its pressure drop characteristics and expansion characteristics, is something that we should look at closely. The other aspect that we have been kind of assuming everywhere here is again sphericity. Now in the case of particularly a packed bed, many of the catalyst particles that you use are not necessarily spherical, and there is also an issue in terms of the fluid itself. When you have fluids that contain droplets or bubbles, they can change shape quite significantly over time, and also as various drag forces and other forces are applied to them. For example, if you can see raindrops, right? Raindrops are a classic example of where water is falling in the form of a droplet through air. What is the typical shape of a raindrop? Is it elliptical or is it spherical? Any idea?
Spherical.
It actually depends on the size. It depends on the intensity of the rain. If you have a very, very fine rain or mist, the droplets are spherical pretty much, because the finer the size of the droplet, the surface energy characteristics take over. You want to minimize surface energy, and a spherical shape gives you the minimum in surface energy. So a very, very fine droplet will almost always be spherical in size. But if you have large droplets that are falling through either as rain or in whatever form, you will see that you get a very distorted shape over time, and that again is going to change its flow characteristics. A spherical droplet will flow with very different characteristics compared to something that is non-spherical, but you cannot again always say whether the spherical body will move slower or faster, because once you start elongating it or compressing it and you have a non-spherical shape, the key parameter becomes the relative orientation of the droplet or particle or whatever to the general direction of flow. For example, if it is something that is just falling due to gravitational force, initially you may have a spherical droplet which will be falling with a certain velocity, but if it keeps getting compressed and it assumes a, say an ellipsoid shape, and the teardrop shape as they call it, then clearly its direction of alignment is going to make a big difference to its settling characteristics, because drag is based on the surface area that is perpendicular to the flow, right? So in a configuration which minimizes the projected area that is perpendicular to the flow direction, you are going to get minimum resistance to motion. So a droplet that is like this will fall quickly, whereas the same droplet, if it is horizontally aligned, will move slowly, and that is just based pretty much on projected particle area characteristics. Now in the other case where you have a packed bed that has particles, again you can have two situations. One is spherical particles comprising the bed and non-spherical particles, and there are some again distinct differences in the behavior, and it has more to do with the formation of channels through the bed. The packing of a packed bed is very different depending on whether you have spherical particles comprising the packing or non-spherical particles. So in the case of spherical particles, so if you have a packed bed and you have, let's say 100% spherical particles versus a packed bed that you have where you have a mixture of different shaped particles and so on, which do you think will, let's say for the same mass of material that you have packed into the bed, which do you think will allow more pathways for motion of the fluid? Is it the one where you have all spherical particles, or is it the one where you have a variety of shapes? In other words, which configuration is more accommodating, where the particles can slide against each other and minimize the void fraction? Spherical? Actually, it turns out that a spherical particle, if you have perfectly spherical particle, they can only have point contacts, right? And so the way that if you shake this loose, I mean if you shake this and allow the particles to settle into a stable configuration, and then you look at the void fraction that's available for fluid to flow through versus one in which you have variety of shapes, it's interesting that in a majority of cases this configuration actually settles in a much more cohesive fashion, because it's kind of more accommodating in a way. The area of contact, potential area of contact between adjacent particles is actually greater in an apparatus that has multi-shaped objects compared to one that has all spherical particles. So what you will find is, if you are flowing fluid through here versus through here, while you are still in the packed bed mode, you will find that the pressure drop will actually be greater here compared to here, because you are trying to force fluid through. The pressure drop will be more here compared to here, because the bed itself is more conforming and allows fewer passageways, whereas in the case of a bed with all spherical particles, it's more possible to have many pathways for the fluid to move through. However, once you get into the fluidized mode, the difference between a bed that was originally packed with spherical particles and a bed that was originally packed with non-spherical particles tends to be very different, because now what you're really looking at is the flow characteristics of spherical particles in a fluid. In other words, now the particles are in motion. In the previous case, we had considered the particles to be fixed in place and the fluid was trying to move past them. In that case, the difference was primarily due to the way adjacent particles accommodate each other and allow or don't allow flow passages. But once you get into the fluidization mode where the particles are actually moving, the difference now becomes the drag characteristics of spherical particles versus non-spherical particles. So a lot is now going to depend on whether there is sufficient room and sufficient time for particularly the non-spherical particles to achieve different orientations and thereby present different areas to provide resistance to the fluid flow. Also, if you look at the size characteristics, in which size range would spherical versus would shape have a greater effect? Would shape play a greater role if you have very fine particles, or would shape play a greater role if you have very large particles? Any ideas? Shape actually has greater influence when the particle size is larger, and the reason for that, of course, is that very fine particles again almost behave like, if you go down to the nano sizes, they behave like vapor molecules in general. So that ability to interact with each other and accommodate each other is much greater, and it's virtually independent of shape. But as particle size increases, its shape also becomes an important characteristic. For one thing, you really cannot separate the two anymore. When you talk about the size of a large non-spherical particle, there is no unique size, right? It all depends on, again, the orientation to the flow direction. It depends on how you sample it, what method you use to measure it. So it's very difficult to define a unique size for a large particle, and therefore the interdependence of shape and size becomes even more pronounced when you go to the the larger sizes. So, these are some interesting aspects of operating a packed bed versus a fluidized bed, and the various impacts of particle size and shape and so on. One of the critical parameters in the operation of a fluidized bed is the minimum fluidization velocity. So, in the next class we will talk a little bit about how the minimum fluidization velocity is derived and what is a safe operating point. You know, how far should you be above or below the minimum fluidization point in order to operate your column in the way that you want to. Any questions? Okay, see you in the next class.